Welcome to a tutorial on the 8085 data transfer and copy instructions. Okay, so from here onwards we're gonna learn about the entire instruction set of the 8085. Okay, so let's just divide this page into a few columns. So first we're gonna start with the data copy instructions. Now there are two instructions under the data copy instruction types. So the first is known as MVI. Okay, so this instruction stands for move or load 8-bit data into a specified register. Now this specified register that you can see over here serves as the operand of this particular instruction. So we write here the specific register. Okay, so this is where you just mention the name of the specific, you need to specify the register's name over here. Okay, so this is where you just give you a specific register, and the 8-bit data also serves as the other operand. So let's just move this to a little bit on the left. There you go. And next you just give your 8-bit data which you want to move or load into the register that you've just specified over here. So let's just try out an example. Let's say we want to load a data byte or an 8-bit data of, let's say, what can it be? Okay, 2BH into the register C. So we can use this instruction to do so. We can just write here that about MVI, okay, C comma 2BH. Sorry, not X. My mistake, don't mind. So there you go. So with this instruction, whenever we just give this instruction over here, then the register C, well, I don't know what the content of the register C was prior to executing this instruction, but as soon as this instruction gets executed by the 8085, this 8-bit data moves into the register C. Or you can also say that it just loads itself onto the register C. So now register C's content is 2BH. Now this is a very important and widely used instruction for loading 8-bit data. Okay, and well, it also has, it's more precise to specify it as well. Move or load 8-bit data immediately. Okay, so you can just use this instruction to load the data into a register instantly, even if you haven't loaded this particular 8-bit data into any other register or in the program somewhere. You can just use an MVI instruction and just on the spot load the data into a register. Okay, so that's how you can use it. Okay, now the next type of data copy instruction is the move instruction. Okay, so this instruction MOV will actually refers to move. Okay, so it just refers to moving a byte of data from one register to another. So the operands of this instruction are the registers itself. Okay, so where you can see that, well, there are two types of registers mentioned here. One is RD and the other is RS. So RD stands for the destination register, that is the register to which you're supposed to send your data byte, and RS serves as a source register, that is the data byte which is, this is actually, RS is actually the register which contains the data byte beforehand. Okay, so this instruction actually says move the data byte to destination from source. Okay, so let's say if you have the register A, okay, containing a data byte of, let's say, 0CH, okay, and you want to just load this data byte into the register B, which is currently empty. So what do? You just use this particular instruction here. You're gonna write MOV. Okay, now since we're supposed to transfer the data byte from the register A, so the register A actually contains the data byte beforehand, so this acts as the source. So this is the source here. Okay, and since we are transferring the data byte to the register B, so register B serves as the destination. Alright, so we're gonna write here move B comma A. So move to register B from the register A. So whenever this instruction gets executed, we'll see that the data byte gets transferred to the register B as well. You can see over here. So now after this instruction gets executed, the data content of both the registers A and B, okay, both of them just contain the data byte 0C. So in a way the data gets copied. Okay, so basically the data byte gets copied. Okay, so this is a very important feature of the 8085 instruction set. Now other than transferring the data bytes to and from the registers, okay, we can also transfer the data bytes from a memory to and from memory locations. So for the move, okay, as for the move command is concerned, there are other two variations also, and they are just declared somewhat this way. Well, move M comma RS and move RD comma M. Okay, now let me just elaborate. Here M actually what refers to any kind of 16-bit memory location loaded in the HL register pair. So let's say for example if the HL register pair contains the memory location alright 20 FFH. If this is the 16-bit memory location, okay, it could be, it's just a 16-bit data, can correspond to any memory location on the external chip. That's the external memory chip concerned. So if this is an external chip's memory location, a 16-bit memory address, okay, loaded into the HL register pair, okay, so I'm just gonna write that down over here. So in that case what happens is that this particular 16-bit memory address is referred to as M, where M stands for memory. Okay, so this just corresponds to memory locations. So we can basically use this symbol M, okay, that just acts as either a source or destination location depending upon where we declare M, as you can see in these two commands. And then we can use the move command along with the M symbol over here, so which just corresponds to the memory location stored in the HL register pair, and by doing that we can just exchange the data bytes between that very memory location loaded in the HL register pair and a corresponding register. Okay, so let's give you an example over here. Let's say we have the HL register pair was stored with this particular memory location concerned, and now we want to transfer this data byte 0CH from the register B into the memory location 20 FFH. So what do? We just write the command somewhat this way. So first, writing the command, identify the source and the destination. So here, since we are transferring this data byte 0CH from the register B, okay, so here B now would serve as the source. Okay, don't confuse it with the previous case. Okay, now here the register B serves as the source, and the HL register, the memory location loaded in the HL register pair, that is 20 FFH. Okay, this is memory location on the external RAM chip, which has 8-bit registers and can store a byte of data. So this memory location acts as the source, the destination over here, not the source. Okay, B is the source and this is the destination. So whenever you write the command, okay, move M comma, now you're supposed to transfer it from B into this memory location. Okay, so you're supposed to write M comma B. So what happens after this is that the data byte from the register B gets copied into this particular location. So now you can see that this data byte 0CH is present in 20 FFH as well. Okay, so this is how this instruction basically works. And the reverse is also possible. Okay, if you let's say the register C, okay, let's just take it this way. The register C is currently empty and there's nothing. So if we want to move the data from this memory location into the register C, then of course the register C becomes our destination. Okay, and this memory location becomes our source right now. Okay, now let's just forget about the previous example, don't just confuse it. Okay, so now what do? We just perform the reverse operation. We just do it the reverse way. So we write move the destination first, that's the register C, comma the source, that's the memory location. So M. Now since this is already loaded in the HL register pair, as you can see, so we can just refer to it as M. Okay, now this just causes this data byte, that is 0CH, to transfer to the register C, and now we can see that C also contains the same data byte. So that's how you can communicate with memory addresses and the registers, and then transfer data bytes between them using the move command. And similarly, the MVI command can also be extended to that very same domain. Only the instruction would just undergo a little bit of change. Instead of the specified register, we're going to use the symbol M. So again, if the HL register pair, okay, like in the previous case, it contains a memory location, let's say 20F2H, okay, then we want to transfer, but this is M currently, okay, referred to as M. Now we want to transfer at this very location a data byte of I don't know, let's say yeah, we can just transfer this data byte, that is 2BH. Then what do? We just write the instruction somewhat this way. We just write MVI, that is M, okay, then sorry, no comma after MVI, and then we can write M comma yeah, the data byte 2BH, which we had previously transferred in the register C. So we can write 2BH. Okay, now what this instruction would do is that it would just transfer this particular data byte, okay, directly into this memory location instantaneously, I mean instantly. Okay, so you'll find the data byte 2BH loaded into this very memory location once this instruction gets executed. Right, so this is how you can just use these two commands. Okay, and the MVI command is basically a 2-byte instruction where we have 1 byte designated for MVI and the specified register or the memory location, and the other byte for the 8-bit data that we are supplying along with it. Okay, I mean that's being loaded into the corresponding location. Okay, and then for the MOV, that's the move command, we have, I mean this is just a 1-byte instruction. Okay, it's only the byte is designated mainly for the entire statement that you can basically see over here. Okay, so whenever you load these two instructions in the external memory, okay, MVI consumes a memory space of 2 bytes, while MOV would consume a memory space of just a single byte. Okay, now after this we got, oh, and one more thing I just skipped over here is that for both the move instructions, that's MOV as well as MVI, okay, their operands are basically the registers. Okay, so all the registers, okay, that you can basically see that starts from A and to L, okay, all these registers and as well as the memory location loaded in the HL register pairs termed as M, okay, they are all its corresponding operands. Alright, so now we move on to the data transfer instructions. Okay, there you go. So the data transfer instructions will actually include 2 instructions, that is in, okay, for input, and out for outputting corresponding 8-bit data. Okay, so whenever we're using the in instruction, okay, if we would provide in, okay, if you just write the corresponding code as, let's say, in, and give the name of a specified 8-bit port address. Okay, if we just give any type of 8-bit data over here, which is the address of an output port or an input port, sorry, in this case, then what happens is that let's say if we have an input port, let's say we're using the 8255A chip. Okay, let's just illustrate this process with an example, and we're using its port A as an input port and port B as an output port. Okay, so if we write the instruction over here in now the code, the 8-bit code for the port A is 80H, okay, and for B it is 81H. Okay, so if we write in 80H, okay, similar to the input instruction over here, then what happens is that the accumulator, okay, the accumulator register is loaded with the data byte that is present at this input port. Okay, so let's say if the data byte at this input port is let's say FFH, okay, then this FFH is just loaded into the accumulator whenever this particular instruction is executed. So the data from the input port, okay, of the 8255A PPI chip is loaded into the accumulator with the help of this in instruction. All right, and now if we want to execute or basically show the use of the out instruction, then we might use the port B, since we have designated this port B as an output port. Well, we have just assumed it that way. So if we now well, the accumulator has the data byte FFH. Okay, so now what we want to do is that we want to send this data byte, or rather we want to output this data byte through port B. So we write the instruction out and give the port B's corresponding address, okay, 8-bit address. So we write here 81H. Okay, and what this does is that the port B is just sent, the port B would have, okay, if this is port B, okay, then the port B well actually would contain right now the data byte of FFH. Okay, so if you'd have 8 LEDs connected to the port, each pin of port B, okay, then you'd see all of them lighting up as soon as this particular instruction gets executed. Okay, and this particular data FFH is just sent from the accumulator into the out through the pins of port B. Alright, so that's what the output instruction does. It just sends the 8-bit data from the accumulator to the specified port address. Okay, so that's the entire operation of the input and the output instructions. Alright, and for all these instructions that we have just learned so far, for all of them the flag register bits remain unaffected. So you can see that for the data copy instructions as well as the data transfer instructions, they don't affect the flag bits anyway. Okay, now next comes, oh, and once again let me just remind you that well, both the in and out instructions are 2-byte instructions correspondingly. Okay, you always need to keep that in mind. Alright, so now let's just move on to the last part of this tutorial. Okay, here we are. Now this contains two basic machine control instructions. One is the halt or stop, okay, whose mnemonic or opcode is HLT, and the other is NOP, meaning no operation. Okay, and you can see that both of them do not have any kind of operands. Okay, they are just machine control instructions. Okay, and furthermore let me just tell you that well, both these instructions, well, they are just single byte instructions. Okay, and now the question is, well, how do we use them? Now whenever we need to stop a program, okay, from moving further, then we always declare the halt command after the program. So if this is your main program body, so whenever you need to end the program, you just declare halt somewhat this way. So this would actually well end the program. So this just ends the program that you've been executing so far. So whenever the 8085 would encounter the halt command, then it'll know that this is where the program ends. Okay, so that's halt. And now for NOP. Now let me tell you, whenever you declare this statement NOP in a program, then the 8085 basically does nothing whenever it encounters this code, okay, or this particular command. So here what the 8085 does is that it does no operation. Okay, meaning it just does nothing and just sits there for some time. Now in a way you can say that this NOP operation is basically the smallest possible delay instruction that you can give to the 8085. So this is basically the smallest possible delay instruction, okay, that can be given to the 8085. Okay, and let's say if you're operating, if the clock frequency of your 8085 system is basically let's say 3 megahertz, okay, let's say if your clock frequency is basically 3 megahertz, okay, then in that case your clock period, I mean each t state, so one t state is gonna be it's gonna be, well, okay, 1 by 3 megahertz, that is equal to a 0.33 microseconds. Okay, so that way what will happen is that the NOP instruction, let me just tell you, this NOP instruction, well, actually this contains, I mean this, in order to execute this instruction, the 8085 consumes 4 t states. Okay, meaning it just consumes 4 clock periods basically. So here 4 t states, meaning, well, one t state actually corresponds to a clock period. So that's one clock period. Okay, and here this one t state, so this is actually one clock period. That's the measure of one clock period. Okay, that you can get to see over here. Alright, so now whenever the NOP instruction is executed, then since it the 8085 will takes up 4 t states to execute this instruction, then this means that we get a total delay of 4 times multiplied with the time required for one t state. So that's 4 times into time, okay, elapsed for one clock period. Okay, one clock period, there you go. So your one clock period is basically 0.33 microseconds, so which is equals to 4 multiplied by 0.33, that is roughly about 1.32 microseconds. Okay, so you get a delay of 1.32 microseconds by executing the NOP instruction once. Okay, and this NOP instruction is basically useful in either introducing a very short time delay, okay, in the 8085 operational cycle. Okay, so in some applications you might need that. Okay, and also it helps to reduce error. Okay, if you just committed any error by writing any wrong or unnecessary code or instruction in your program, then what you need to do is that you need to, once you detect the error, you need to reassemble the program once again. So if you would just substitute the wrong programming code with an NOP instruction, okay, so 8085 doesn't do anything within that time. So that way your program, I mean your effort of reassembling the program is saved. Like for example, let's say you had a jump on no zero statement, okay, and then you have let's say a DCR statement. Now you're not supposed to give this DCR statement at all. Now you detected that this was an error. Okay, now what do? You'll just need to substitute it. Now you loaded the corresponding the DCR instruction into your memory location. Now what you need to do is that you need to go to the memory location, okay, get your program once again, and just delete the DCR statement and put an NOP instruction over there. Now since DCR was unnecessary, so here NOP just saves your effort of reassembling the program once again. Okay, so that way you can just minimize error. So if you need to manually reassemble the program, well, you might commit any kind of error. So that's quite taxing. So this is two very common ways of using the NOP instruction to a very large extent. Okay, so with that we just come to the end of this tutorial video, and we're going to see you next in the forthcoming ones once again. Okay, so till then, just bye bye for now.